Okay, hello everyone. I too was going to do a science talk and realized, oh, that's not correct. I changed, so now I'm talking about the code that enables the science. I'm going to be talking about my ray tracing code, Krang.jl. So what is Krang? Krang stands for Kerr Ray Tracer for Analytic Null Geodesics. So it's kind of different from a lot of existing ray tracers where they kind of allow you to implement whatever metric you want. This is very specified for the Kerr spacetime, and the reason for that is because the Kerr hypothesis seems to be correct, and if you want to fit data, you want your algorithms to be as fast as possible. So there's a lot of speed up that you can benefit from by just assuming the Kerr hypothesis for the black hole. In particular, since I'm a member of the Event Horizon Telescope, and there's specific phenomenological features associated with images of black holes that we care about, particularly sub-images, by essentially encoding a ray tracer that uses analytic algorithms that allows you to more efficiently decompose images into sub-images and so on. I'll go on to show an example of what I mean by that if you're unfamiliar with the idea of sub-images from around black holes. The other benefit of coding things analytically is that if you use ODE solvers, you get an approximate solution. And if you care about derivatives, then whatever order your approximation is for your solution becomes a lower order for your derivatives. But if you use analytic solutions, you kind of have the exact answers for your derivatives. So there's that additional benefit. Okay, so what does Krang get you? It's GPU compatible. So if you want to ray trace on a GPU, it's got you there, got you covered. It's also is automatic differentiable, mostly through enzyme.jl, partly because that's kind of the easiest one to implement, and also partly because I work a lot with Paul and the interface with Comrade a lot. Okay, so why Krang? The main goal is for using it for studies of black holes. So we know that black holes exist. We know there's a lot of evidence for black holes. We see emission from blazars and quasars. We see compact X-ray sources. We see large radio jets, and some other things that people speculate could be black holes. For Krang in particular, the way how it works for ray tracing these images of black holes is that I kind of embody this philosophy, and this philosophy is not really unique to Krang. It's kind of common in a lot of ray tracing codes that exist out there. But the idea is that Krang ray traces what are called meshes. And meshes are just some composite of a geometry and a material. And the idea is that the geometries encode where emission is being emitted, and the material is just local physics. Physics, one of the important concepts of physics is that everything is local. So this decomposition kind of is embodying that philosophy. So in Krang, there are three main geometries that have implemented so far. There's this conical geometry, which I'll show the reason for why that's there later on. There's also this level set geometry, which is kind of a more generalized version of the conical geometry. And then there's this mesh geometry, which is just, you can essentially import a STL file like one would use for 3D printing, and it just drops it in the Kerr spacetime, and you can ray trace that. So that allows you if you have some weird accretion flow around a black hole, you could design something strange in order to model that. The materials in general, just how one defines the local emission physics necessary to render the geometries on the screen. Okay, so what can you do with Krang? So this is just an image showing just some rays that are coming in from these are the rays that lands at some observer that's looking at the black hole at a nearly equatorial view. So let's look at that conical geometry that I mentioned at first. So the conical geometry is a spin axis centered cone with its apex that's placed at the coordinate origin. So this is just showing what happens if you take that cone and open it up around the black hole and then close it out on the other side. This is what it looks like when ray traced. And furthermore, I'm showing you the image of said cone decomposed into sub-images. So whenever you look at the source around a black hole, you get a single image of a source can be decomposed into multiple sub-images. And those sub-images correspond to how many times light has wrapped around the black hole before it reaches you. So at the top, I'm just showing the most direct sub-image. So light did not wrap around the black hole. The middle shows the first indirect sub-image, so light wrapped around the black hole once. And then the bottom shows the second indirect sub-image. And as you can see, as it wraps around the black hole more and more, it gets thinner and thinner on the screen. Okay, so that's geometry. So let's talk about materials. So implementing materials is very easy in Krang. In general, it's just a functor. It's a functor that needs to be a subtype of abstract material. That's basically it. This is just an example of a material that essentially returns an emission of 1 whenever the ray intersects the geometry. So that's all it is. And if you took, say, that same cone geometry that I showed before and just asked to ray trace the direct image and the first sub-image and you were looking down at the cone, like you're looking down through the apex of the cone, then this is the image that's rendered through that. So you get a white band where rays had intersected that geometry twice, and you get an orange band where it intersected once. Okay, and of course you can define other, one of the reasons that this decomposition is helpful is that oftentimes you tend to think about, at least in the EHT, we tend to think about the emission geometry that's very separate from the emission physics. So one could say swap out that X material emission physics and pop in a more physically realistic emission physics. This is just an example of a synchrotron emission model with a power law electron distribution, and as you can, and that exact same image that I showed before gets modified by quite a bit. Once you encode the physics, you actually get something that kind of looks realistic. And this is just showing the said same geometry ray traced with this accretion material to give rise to Stokes signs, Stokes Q and U parameters. This material to implement it has no Stokes V. So I mentioned that's a code geometry. Now the level set geometries. The idea of a level set geometry is that suppose you want to implement some surface in there, and the surface has a nice mathematical description. If the surface is defined by a level set, then I got you covered. So it's very simple to implement. This is just an example of a paraboloid where essentially, again, it's just a functor, and it just needs to subtype abstract level set geometry. And as you can see, all it just does is return that function. It just returns that function, and wherever that function is 0, it will ray trace that as an intersection. So if you took that same X material from before and ray traced it for that paraboloid around the black hole, this is what it looks like. It looks like a paraboloid, and then you see the photon ring there. That's the first sub-image. And again, everything is modular. So that's just the code for the paraboloid. I can just take the same synchrotron emission model that I wrote before for the cone geometry and just apply it to this paraboloid, and once doing that, then you get something that looks even more realistic. So I think that's kind of been hard to model. That is often talked about are jets that have limb brightening here. You can see that if you just say take the synchrotron emission and you kind of get the things right, you can manage to get limb brightening. Yeah. And the last one is the mesh geometry. So I'm just going up in levels of abstraction. So this is just like if you don't have a function, you just kind of, I don't know, you're good at Blender or something. and you can just draw the thing that you want to represent. So this is an example of the Stanford bunny. You can just use geometrybasics.jl to import it. If I drop that bunny in the space-time and just put it in front of behind the black hole and ray trace it, this is the image that you get. And of course, I can drop a synchrotron emission on said bunny, and you get something like this. The electron distribution is kind of flowing. I'm not sure how this is on the. Yeah, it's flowing this way. So the side where it's brightest is just where things are boosted, Doppler boosted towards you. Okay. So now that's just a gist. That's an overview of what's going on. So now for the science cases. So a lot of these science cases. There are additional science cases beyond what I'm going to show here. These are just kind of the science cases that I've used my code in particular to work on. So the first is this Bayesian black hole photogrammetry paper. So just quickly, I'm going to summarize the background. So the EHT produced the first image of the shadow of a black hole from observations made in 2017. The image came out in 2019. Those are the images I showed below. Sorry. And the analysis that was done for these images involved various model fitting techniques. And the models we tend to bucket them into two categories, either geometric modeling or imaging. And the idea of imaging versus geometric modeling is that the imaging models are very flexible, but it's hard to perform inference with them. whereas the geometric models are quite inflexible, but they have a very precise interpretation. There is, however, a caveat to the geometric models, which is that they are a model of the image on the sky and not a model of the bulk space-time itself. Like, they're not actually a model of the bulk accretion flow. So even if you do geometric modeling, in order to extract information about the system that you're looking at, there's some additional steps that you have to take. So in particular in the EHT, they do various things like an alpha fitting procedure. They try and use the geometric models kind of as a bridge between their expensive general relativistic magnetohydrodynamic simulations and the data that they're observing. The long and short of it is just that the geometric models do not directly give you information about the system that you're looking at. So then there's this idea of photogrammetry. So what I'm implementing is not precisely photogrammetry, but it's in the spirit of photogrammetry. So the idea of photogrammetry is that you have some model for the way that objects kind of, their surfaces appear in space. And then you have multiple images, and then you want to fit the images with your model in order to figure out what the arrangements of those, of the facets or the meshes should be, and the various materials on said model should be, in order to extract 3D information from the image. So as the name implies, you're measuring stuff from photos. So in doing so, you take that same cone model. So this is why the cone geometry is implemented in the first place. You can just define a simple toy model for what we think the 3D structure around these low luminosity AGN, like the ones that the EHT looks at, are like. Essentially, this model is just a Kerr black hole. The idea is that we think the emission is probably coming from the jet walls. If it's not, it's probably coming from a thick disk. So we just treat it as a double cone. It's fairly compact. So the exact shape of the jet wall doesn't really matter too much. You know, if you Taylor expand, everything looks linear. And then we ray trace that. We think the emission is synchrotron. If you do that, you can then fit said model to the EHT data and extract information about the bulk spacetime. Now, in order to actually fit the model to the EHT data, we have to, the Krang by itself is just a ray tracing code, so you can interface it. The modularity of Julia allows this to be very easily interfaced with Comrade. So just an example, if I define the jukebox model from that cone image that I showed before, it's just a couple lines to put it into Comrade. I just have to define what the intensity point is. It's a ray tracing code, so it ray traces to a point on the screen, and that's it. This is just all you have to do in order to interface it with Comrade. Okay, and once you do that, you can actually fit it to data. So this is just showing an example of said dual cone model fit to the 2018 and 2017 data. And you can see that once blurred to the EHT resolution, so the EHT image is shown on the bottom, and the model fit blurred to the nominal resolution shown in the middle row, and you can see they look very similar. But the models are also allowing you to get extra high resolution information that you may or may not believe, depending on how much you trust that. I can go into more details about that later, but just with respect to the code, one of the things that's beneficial about that, if you look here, this model has like 13 parameters, right? So one thing that all the people in EHT are interested in is what image features, like what features on the screen tell you about the bulk space-time parameters that you wish to study. And one of the things that's kind of nice about Julia is that I was able to make this automatically differentiable. I didn't really have to do anything. I just put enzyme into that, it works, and I'm able to create these saliency maps like people do with machine learning models, and I'm able to probe what features in the images are sensitive to the bulk parameters. So in particular, you can see that in the top row, the photon ring is evident, that like sharp ring feature, and the three things that stand out, the three parameters that are most sensitive to the photon ring are essentially the black hole parameters, the mass spin and the observer inclination with respect to the black hole spin axis. So that fits along really well with the narrative that people have mentioned before. Okay, so the next science case, there's future VLBI experience. My advisor has been working on a potential space VLBI extension to the EHT called the Black Hole Explorer mission. And the idea is that this will help us get higher resolution images of a black hole. As I mentioned before, if you look at the saliency map, it seems like the photon ring is what is sensitive, or it seems like the photon ring is sensitive to the black hole's parameters, so the mass, the spin, essentially the space-time parameters. So what this implies is that if you have a really high resolution image, it should allow you to take very accurate measurements of the black hole space-time itself. In particular, if one is able to resolve that photon ring, then you should be able to do a black hole spin measurement. So it seems like there's this potential avenue for new black hole spin measurements that are agnostic to the black hole accretion. So again, I bring up this imaging geometric modeling approach. So if one were to do this, it'd be very hard because you kind of need to understand how to tie the black hole's spin parameter to the image features that you're looking at. But there's also this other issue, which is when I showed before the 2018 to 2017 fits, as you can see, the black hole looks very different between 2018 and 2017, or sorry, the fits look very different. But Krang, this geometric model itself is a model of the average accretion flow, and what this implies is that if you were to fit a model of the average accretion flow to data from different years, the variability in the years is appearing to order 1. It's kind of influencing your fit and causing your parameters to sway a bit. Not everything sways, but a lot of things sways. So the ideal situation is to kind of fold in this variability into the model itself. And the approach is that we're doing this kind of hybrid geometric modeling approach that encompasses that dual cone that I mentioned before. So the idea is that the dual cone model represents the average state of the system, and then we include an additional variability model which we multiply that dual cone model by in order to account for the turbulent accretion flows that generates differences in images. So what I'm showing here is just said model, and these are just random draws from the prior. So I'm just like drawing random things from the prior, and as you can see, they all kind of look like black holes, but they also have weird fluff around them. So this is just kind of a next step improvement. And this is very easy to implement. It was just, I didn't really have to write any new code. I actually just took Paul's imaging model and literally put it in the bulk space-time and ray traced that instead. Yeah, so as just summarizing that, the idea is that jukebox is a good representation of the average image state. Simulations imply that variability due to turbulence affects your data up to order 1, so we want to incorporate that variability into the model. And this is preliminary, but this is just showing an example of said model fit to the 2017 data. So what's interesting, so again, I have the EHT 2017 image that's shown there. The consensus image in the middle, I have this from the literature, this primo image that's generated from doing principal component analysis under a GRMHD assumption. And on the right, I have this variability model, which is very, very flexible. So it doesn't make any assumption about GRMHD or anything like that. It can produce on aphysical images if it wants to. I think the thing that's kind of interesting about it is if you just look at it, there's certain features you can see. There's this brightness asymmetry that's kind of consistent. Oh, I think I put the wrong year. This is this is the wrong year's image. This is 2018. It should be this image. I'm fitting this year, the 2017. So the brightness asymmetry is there on the bottom left. So you can see that matches here with this variability model and as well primo. All the images feature shadow. But I think something that's interesting is this feature that's here on the southwest. Now, one of the things that's kind of nice about you interfacing this with Comrade is that one can do a Bayesian analysis. So, this is just a single draw from the posterior, but one can actually just look at samples from the posterior to see if any of these features are consistent or not in order to determine what we can actually say from the data and what we can't. So in particular, I'm just going to show a movie of the snapshot. So this is just showing draws from the posterior. You can see there's quite a bit of variability. And the point being is that each draw here is consistent with the EHT data. Each draw here is a possible instantiation that the system could have been that would have given rise to the data that we observed on that day in 2017. And the thing that's interesting is that you can see the photon ring moves in and out. Sometimes it gets dimmer, sometimes it gets brighter. So it's evident that we can't really constrain that too much. But there are certain features that are consistent. So in particular, we see that shadow is always there. We always see that brightness asymmetry, and we always see this fluff. And I think this fluff is particularly interesting because You know, MH7 has a jet. The fluff this might be a sign of the jet wall. It may not. It could just be some fluff. Who knows? I think if I fit other years and we see that fluff persist, then that'll tell us about that information. And then this brings me to the last thing I'd like to talk about, which is multi-frequency jet modeling. So Randy had worked on multi-frequency imaging, and I think it's a good idea to kind of fold that into these existing models, which is again easy to do because of the modularity of Julia, but also put it into the bulk spacetime to just figure out what's going on. So recently there's been some advancements towards imaging the jet launching region of the black hole. So in particular, there's this Kim et al. Paper, which seems to suggest that we are now able to see where the jet is launching from the black hole shadow itself. So you can sort of see, you know, you see a dot, you see a shadow, and you see the jet attached to it. But strangely enough, the 230 gigahertz image from the EHT does not show this feature. But it might be there. It might just be that we need more robust models and better priors in order to extract that information. And I kind of flashed this geometric model again. I think this is kind of the avenue to go forward in order to understand what's going on in that system. So I think the benefit of this over some traditional approach like GRMHD is that you can just easily swap out the material, can just easily swap out the geometry, and just see what is consistent with the data and what tells you what's going on. And that's it. Thank you. If anyone, that's my GitHub link to Krang. If anyone has any questions, please don't be afraid to ask.
Fantastic talk. This is really, really interesting. For the ray tracing part, are you able to utilize the traditional graphics pipeline units in GPUs, or because this is ray tracing, different kind of geometry, you just have to do it manually?
Yeah, so it's where so Julia only has access through the compute shaders. They only write wrappers for the compute shaders essentially, but it doesn't matter. It gives you the same performance, just that you kind of have to approach a problem a little bit differently from how you would with a normal graphic shader, but it kind of doesn't matter anyway because a graphic shader would render to the screen, so it wouldn't be too useful for you for scientific analysis anyway. But yeah, it's essentially just the same as, well, I'm not actually writing in the shader language, I'm just using, it's essentially just you import a CUDA array or a metal array and you broadcast over it.
So maybe I haven't fully understood what you showed when you showed the saliency map, but is it possible to show a saliency map marginalized over something that you don't understand in your Bayesian model, and as an extension then make better choices about what visibilities you really need to prioritize to improve your posterior estimate on the parameters of actually interest?
Yes, that is, sorry, I'm just looking for it. That is true. I think, so this saliency map was kind of constructed because I think it was just sort of, it was constructed out of this want of if someone gave you a picture of a black hole and, so you wanted to point to them at a feature to study in order to extract some information about accretion or something, what would you look at? So this is kind of the most agnostic thing. I think in principle you could pick specific directions in constructing the saliency map and marginalize over variables in order to get more, I guess, accurate features under certain assumptions. Yeah.
But could the saliencies be propagated all the way back to visibilities as opposed to the image?
Yeah. So it can okay. Maybe I misunderstood the question. So this is a saliency map in image space. So what I could have done is that I could have constructed a saliency map in visibility space. And yes, it would propagate that way, yes.
Yeah, this may be incorrect. Have you ever thought of using geometric algebra and to do your calculations.
Geometric algebra?
Yeah.
No, I've never.
And conformal geometry.
I haven't tried it. No, I should. I'll
And,
try and give it a
you know,
look.
there's Geometric Algebra for Physicists by Chris Doran. He gave a talk a couple of years ago at
Yeah,
JuliaCon
yeah. I
about
think,
how he's trying to use geometric algebra to improve ray tracing.
yeah, I know you've mentioned it before. I keep forgetting to look it up, but I should look it up.
All right, let's thank Dominic again.